So the three primary conceptual ideas that I wanted to discuss today are that discussed here, essentially mostly focused towards some advanced heatsink development, and that is based on geometry modification. So while you can do what are called active heatsinks, where some member of the heatsink, some element in the heatsink is actually moving actively, like a piezoelectric fan or a system of that kind. That I am going to not discuss much, but what I'll discuss is something on three basic ideas, which is first idea is array of ducts, where the goal is to improve the surface area and see if we can pack an array of ducts within a given functional volume so that the surface area is increased, so the convective heat transfer is increased. And we do it in a way that at a given fixed pressure drop, we want to see improvement in thermal performance. And the second one is porous materials. Like porous material or anything that you can envision as even the array of ducts can be seen as a porous material. However, what we mean by here is that there are class of porous materials like metal open cell metal foams. I'll show some pictures later, or something like periodic foams that we work in our lab here in IIT Bombay. So where the metal ligaments or the construct of the porous material is continuous and it has a three-dimensional pore shape, and the pore meaning the flow, the area through which the flow will happen is also continuous. So that allows both heat to be conducted seamlessly in a three-dimensional fashion, to have a number of flow obstacles that induce local mixing. Essentially, anytime we have a flow going past a cylinder, you see that it induces a wake region. That wake region induces mixing of wakes if there was another cylinder stacked vertically. So those type of flow induced local mixing of the flow, because usually the hotter air is closer to the heater and colder air is on the top. So if you want better heat transfer performance, we need to make sure that the mixing is happening locally so that cold air and hot air mix, and so that the overall mean temperature rise is maintained throughout. And there is no big stratification in thermal gradients. The third one that I will talk about is laminar flow instabilities, where we induce geometry such that we create the flow, we make the flow unstable, and we make it such that the unsteadiness is sustained passively, not actively. Is made sustained, and we make use of this to ensure that we get very high heat transfer rate, again by mixing. So this is another way of enabling mixing, and we'll compare these three different approaches and see, at least on a common platform, for the range of Reynolds number or velocities that was investigated, how they performed. First, we'll discuss the array of ducts. One second. Um, sorry, there was a phone call. So here's the array of ducts. What I mean by array of ducts, here's a functional volume for heat sinking. The heat source is placed at the bottom, and it is conducted through many of the one example of a structure is shown here. Is that now the heat dissipating heat generating device is kept on the bottom plane, and it conducts the heat through these members, while these openings allow air to flow through them. As you can imagine, you can have rectangles, you can have triangles, you can have squares, you can have hexagons, and so many varieties. The reason for all these are space filling polygons. We can use circles as well. However, the circle will create not uniform thickness of these fins. There'll be sort of there'll be a non-uniform distribution of material around. So we did not explore circle. However, hexagonal shape represents sort of like a circular duct. So one look at it, one gets a picture that okay, this is going to be somewhat complex. However, what one sees is that a very simple um, um, a fin calculation can be performed to get very good results. Actually, what I'm showing next is a situation where we're going to assume that the flow can be assumed to be fully developed through these ducts, and indeed most of the cases will see fully developed flow, because what happens is when you bring the flow and you are dividing that into this many number of channels, each channel receives very little flow compared to a full bulk flow going through a parallel plate type heatsink. So indeed it ends up being more fully developed flow going through these channels. So you start, this is an hexagonal arrangement, but this can be treated as, depending on the angle, one can obtain even straight lines. So here's an example of a hexagonal duct, which is much more involved. So the idea is to treat this as a single fin and then add these elements to make it hexagonal ducts. So what we'll do is, as you may, a simple fin equation is given by this expression, and you note that instead of writing your coordinate in y direction, d square d by dx is y square, we write it in terms of this local coordinate psi. So then that psi can be easily related to y based on its geometry. So what this says is that now I can represent this hexagonal duct heatsink by a simple fin equation, and so for that the solution is known. The only important thing to remember is that one has to assume in a fin equation we always write t minus t infinity, as if there was single fin and there was no, we don't care about there's a large reservoir, so we treat the ambient temperature to be constant. Here we can't do that because the heat is being picked up by the fluid that is going into the page in this case. So that fluid temperature is a function of x, which is the flow direction into the page. That needs to be tracked. However, this is defined in terms of psi square, which is a vertical coordinate. So then one can write the temperature distribution from well-known, this has been well documented in heat transfer textbooks. So that's the expression you will get. That assuming the tip to be adiabatic, tip of the fin to be adiabatic, and the bottom to be constant temperature, you will get this expression that is given here. Then these c sub h are the local coordinates, and I have given their um, essentially some of the constants later in the slide, or I can send it to you. However, once you figure out the temperature, now you can write the flux at the bottom, which is given by minus ks d and dt by dy. So that also can be figured out by using a simple Fourier's law at y equal to 0 or psi equal to 0. Now we need to attach the lateral fins. Essentially, now once I know this temperature distribution, what I need to do is catch this temperature and make that we add a new fin and attach the fin direction to be like this. Once we know the base temperature, now it will spread through this. So now we can add another fin equation and solve for it, or use that can be detailed analysis. But as a first order approximation, people have done this calculation, and there are some constants that one can use. If it is hexagonal duct, the vertical fin, if this is the corrugated fin, then you have to multiply that 1.5 to obtain the approximate relationship as if this duct was. So one important aspect that needs to be remembered is that this local heat transfer coefficient, what to use. Because we are talking about hexagonal ducts, rectangular ducts and triangular ducts, and we are assuming fully developed flow, you can relax that assumption. But for fully developed flow, those duct Nusselt numbers are documented in textbooks. So you have to use hexagonal ducts, heat transfer coefficient, triangle, or whatever the duct shape happens to be. So then one can obtain this final total heat transfer from this, and this is for one unit cell. So we exploit one unit cell of this kind, and like what is shown here. So if this is my, where is the hexagon? Yeah, here. So this is one unit cell that was picked from this window. I can draw that window. Exploiting the symmetry in the design. So here's the hexagonal unit cell that that's how it will have. And if I remove these lateral fins, you will get this corrugation. So that's what this is. So for one unit cell, so depending on the total width of your heatsink, then you will have n number of those units repeating itself. So that needs to be multiplied. However, we have figured out already what should be the heat transfer rate. So that is fin side. How we said that there is a fluid temperature that is also going into the page, so that is picking up the heat from this fin. For that calculation, all you have to do is do what is a simple enthalpy balance. So MCP delta T is equal to, there is two paths for heat to get dumped into the duct. One is through these fins, the other is from the bottom base itself. So that's what is done. So this is a purely energy balance. Ns is the number of unit cells times Q, that is the number of fins, plus the heat transfer directly from the bottom wall. From that, we can obtain the expression for wall flux, and you can define a heat transfer coefficient, and then you can get total heat transfer rate finally for this arrangement. So that is the final expression that one looks for. This is the fluid temperature expression. Taking this and putting it in the total heat transfer, we obtain the final expression using just purely MCP delta. Okay. Then pressure drop can also be predicted using the well-known friction factor relationship. That is also well documented for all these different duct shapes. These geometric constants that are needed is documented here. As you can see, C, A, C, S, N, those are the constants that I have used throughout. And they are, and you can see that triangle has a Nusselt number of 3, square has 3.614, and this is the friction factor and hexagon and so on. So you can even define it for rectangles. Then the friction factor and Nusselt number are given by this. Alpha is the aspect ratio of the rectangle. So finally, if I compare all these ducts, you can see that triangle, this is for a fixed pressure drop of 10 pascals. So if I fix my overall pressure drop across that heatsink to be 10 pascals, so this is what I get. So the triangle shape has the highest thermal resistance, even though there is an optima that exists for the triangle shape itself. Its minimum resistance is still higher than that of the square, than that of the hexagon, and finally a rectangle of aspect ratio of 4 gives the best performance of 1.7. So you can see that depending on the shape, you will get different thermal resistances and different optimas as well. So that is one example of a hexagonal ducts. However, as I pointed out earlier, so the ducts that are closer, if I had my heater at the bottom here, these ducts get much hotter than the ducts that are on the top. Even if the fin efficiency is sort of close to 90%, you still see that top ducts see very lower heat transfer compared to the bottom ducts. So it is better to mix them. So if you induce some sort of if you create some slots vertically going through into the plane and flow is happening through these hexagonal ducts, then these slots create opportunity to mix fluids that are going on the top, and that's what is shown in the figure here. However, what happens is when you create these mixing zones and so on, now this this body now sees two types of drags. One is the skin friction drag that is happening from the top and bottom areas where the fluid is making contact, and the second is sort of very similar to a bluff body or like an aerofoil shape. So you start to see the form drag as well coming into the picture. The flow goes through this, and if you want to reduce the form drag, then you have to make this fin take a aerofoil shape essentially. So people have done all sorts of work around making not hexagonal slots, but making that into aerofoil shape and so on. And the second thing that happens is because of this separation of the flow from the separation of boundary layers from an object, then what you see is that the Reynolds number where it transitions from a laminar to turbulent also happens much earlier, close to 600, Reynolds number of 600. So these are much more involved heat sinks, and they do perform better. I will show later. Um, um, so that's one concept of increasing the geometry surface area to achieve performance, heat transfer improvement. I will compare all these three different options later. Open cell foams. These are some materials. They've been around for now 20, 30 years, but they they have been studied for many applications like heat exchangers, catalyst support, implants, bearings, and energy absorption, sound absorption, and so on, depending on their porosity. A close-up of a stochastic, a randomly oriented pores is shown here, where you can see this is an aluminum porous foam, that this is where heat is being conducted through these ligaments and airflow will happen through these pores. So this is the porous material approach that I am talking about. One of the real advantage of these materials is that they have very high specific surface area. Essentially, surface area per unit volume is very high for these materials because now they can take any of the complex pore shape. And so they have been studied for heat pipes, heat exchangers, flow straighteners, heat sinks, and so on. And we will look into that aspect, but in this presentation. If I look at it from velocity versus thermal resistance in this plot as shown here. Or first, let me give an overview. There was a study by Bhattacharya and Roop Mahajan, where they showed that um, even for a fixed pressure drop, that these foam heat sinks had achieved about 1.5 to 2 times improvement in heat transfer. That is still debatable. However, they have shown where they had fins and foams inserted between the fins. Two, the reason for that is that why should we have a fin like this? Is that these ligaments are very, very thin. Their thickness, approximate average thickness, is on the order of 0.4 to 0.5 mm or even less than that. That means your conduction area is very, very small. So fin efficiencies start to drop because they tend to be very tall, let's say 25 millimeters or above. For heat to transfer from the bottom where the heater is all the way to the top requires that fin efficiency will drop because the locally in the pore the heat transfer coefficient is very high. So you have very high heat transfer coefficient happening at the pore level, and the conduction cross section of the ligaments is very small. That means its fin efficiency is going to drop dramatically. In fact, some of the simple calculations you can do and estimate its fin efficiency, you will find that in many occasions it falls well below 30% fin efficiency. That means what it means is that now we need to create, we cannot make this heat travel only through these porous ligaments. How instead you need to put some fins and conduct first the heat will flow through these fins and then conduct it horizontally where the thickness is shorter. So that's what these people have done, Bhattacharya and Mahajan, where they put a base and then they conduct the heat through these fins and then into the porous foam like this, so that now the fin efficiency is not sacrificed. So what we did in some of my past work is to make, instead of a stochastic foam where the pores are very random, we tried to make what are called periodic foams. An example of that unit cell is shown here. And we found that as a function of thermal resistance versus velocity, you see here some experimental data here, that you achieve extremely high heat transfer rates. So that's why the thermal resistance is very small at equal velocities. Yes, the pressure drop is higher as well, but based on constant pumping power, fin foams, this periodic foams show very good performance. So almost 50% improvement in thermal performance. I hope I'm recording. So that's the fin foam idea that we've been looking at, and when Professor Shripriya comes and I work with her on how to use these fin foam structures as well. So she will be talking about how to design porous structures for absorbing sound as well as dissipating heat within the same functional volume. So the sound absorption. Is there a chat? Yeah. So the sound absorption is also achieved. Sound meaning noise here, is within the same functional volume. She will talk about that in the next session. So that's what this is another heat sinks that we prototyped and tested. Manufacturing was very challenging. However, we were able to do it using 3D printing technology, not direct metal 3D printing, but we started with the plastic part and then did investment casting. And these investment casting is very challenging because traditional investment casting methods allow you to have only feature sizes that are 2 mm or above. So some of these feature sizes can be as small as 0.4, 0.5 mm. We were still able to do by investment casting of our part, 3D printer part, and we showed successfully demonstrated this technology. This is almost 10 years old now. Anyway, so that's that work. So I'll move to
So just 1 second. Here you said that this foam is opposed to the stochastic structure. So could you
yes.
please slightly elaborate? Maybe I missed something there. So how are the porous structures here in this deterministic foam then?
So if you can see this image, can you see this image?
Yes, the metal one, right?
No, not on that. I'll pick a laser pointer.
Okay, okay.
Yeah, can you see this unit cell?
Yes, yes.
So that is the unit cell that gets repeated in all the 3 dimensions. So that's how we make the periodic form. In the stochastic form that is shown here, let me do one thing. Just give me a second. So that's the unit cell. So this was created by taking a cube of metal and putting spherical voids at its BCC arrangement, that is body centered cubic arrangement. We put spherical voids we take a unit cube at its vertices, 8 vertices, and at one at the center. So that's the body centered cubic arrangement. And we subtract that metal by a simple CAD operation. Then we get the structure. And that is the unit cell that we get periodically. And in fact, we have shown back in the, anyway, I have shown that this periodic structure is able to predict the performance of the stochastic form, like shown here. These are the stochastic forms that are available commercially in the market. So we show that the geometries that we create by this periodicity and this are equivalent because we are able to capture the surface area per volume and so on. So that's how, if this unit cell gets repeated in 3 dimensions, then you get a periodic unit cell.
Okay, but you said the performance is comparable, is it? I thought it was better with the periodic.
We were getting better performance than than stochastic. The
Okay.
stochastic had, she will discuss in the next session. In fact, what we observed was the stochastic foam had more pressure drops. In a periodic cell, the pressure drop was less. So overall, the performance of the periodic foam was better than the stochastic foam. But
Okay,
this
okay.
claim made by some other group, Bhattacharya and Mahajan,
Hmm.
where they did stochastic foams. This heat
Okay.
sink is from their work.
So the fin still exists then, which is different from the repeating this unit cell. Is that
Yeah, so
correct?
the fin is here. Yes, you can see. I'll show this. I'll blow it up. You can see the fins here, and we have put this unit cell in between the fins. That I don't know how clearly it is coming across.
Yeah, I'm able to see it, but how many unit cells are there? Like, what is the size of one unit cell?
So this is about 4.5 mm. So this height is 13 millimeters. This length is 32 millimeters, and this width is 32. So 32 by 32 by 13 millimeters, all millimeters. So you'll see that there's about 2.5 unit cells, 1, 2.5 here. So about 13 millimeter high. So close to 4.5 to 5 millimeter unit cell is the height of the unit cell. So 5 plus 5, 10, and about 3, which is almost half unit cell.
Okay, sir. Thank you. Thank you.
Okay. So the next option that is to look at this unsteady flow. So sometime back in there was a group in MIT. They demonstrated that that one can obtain very high heat transfer. Um, this R here is a Reynolds number, and they showed that you can improve heat transfer by making the flow unstable, and making it unstable meaning that it will be an unsteady flow. So for example, in this picture, this is from their paper. They have a wall that is heated on the bottom. The top wall is not heated, and it's a cross section where there is a cylinder that was placed very close to the wall. So for a Reynolds number of 125, there was no improvement or anything, no heat transfer. But however, at Reynolds number of 300, now they start to see that this wall and the fluid is interacting, and you start to see these wavy structures forming. And these wavy structures tend to stay continuously in the unsteady fashion. One wave after another wave keeps coming from a very passive manner, so the flow is not being modulated there. And they showed that this is a Nusselt number heat transfer enhancement, and this is the Reynolds number. They showed that if there was no, this is called, the cylinder in cross flow is called eddy promoter here. When there was no eddy promoter, you see that it is, the Nusselt number is constant. There is no change. However, as Reynolds number keeps increasing, initially up to a certain Reynolds number, the improvement in heat transfer is very minimal or same as the flat, that is as if there was no cylinder in cross flow. Beyond 150 Reynolds number, now they start to see gradual increase in Nusselt number. So now the Nusselt number, they were able to show that up to a Nusselt number of 4, which is almost uh, close to 3x of where they started, which is this. And also they showed that there is a flow rate or a critical Reynolds number where this vertical axis is pumping power. They showed that the pumping power also reduces up to a point and starts to increase, because beyond this point it becomes turbulent flow. So there is an optimum value where this flow needs to be triggered such that you benefit from having these eddy promoters and also benefit heat transfer. So they have shown that this work. So we took some ideas from this work and made our own. I will discuss that as well. But here's an example. For us to make some unsteady flow, this is a work done here at IIT Bombay, where this is a unit cell again, just to show the concept. We bring in some flow, and these are semicircular arcs, and that is a duct. So the semicircular arcs will be period. This is a periodic unit cell, so it gets repeated in 3D. I will show the 3D structure soon. So, but the basic concept is to show that when a flow enters, the flow will separate. That means there will be a dead zones or type of thing here on the top and the bottom. We assume that the gravity has no role in it because the flows are very fast. At some point, as you keep increasing the velocity, this zone here that's separated starts to interact with the main flow, because that main flow is shearing the flow that is sitting here. After some point, to shed vortex into the mainstream. So that is the start of this unsteadiness. So that vortex keeps shedding, and there is a core flow, and I'll show some pictures too. So you can see here, this is a non-dimensional velocity as a function of time. you start to see that around Reynolds number of 500, the flow now starts to show some sort of a fluctuation. Once we go to slightly higher Reynolds number, 665, now the fluctuation starts to increase in quantities. At around 1500, you start to see a very steady, unsteady flow periodically. And at very high Reynolds numbers, then you start to see double periodicity and triple periodicity. Now it is really progressing towards turbulence, and it's actually becoming chaotic at this point at very high Reynolds numbers. So we want to avoid these type of high Reynolds numbers. However, if I look at a snapshot, this is at 1500. This is the isotherm. This is incident. This is one incidence of a periodic fluctuation. So one cycle of that periodic cycle is shown here. At time equal to 0, you can see that the main flow is coming. This separated flow starts to eject out of this pocket into the mainstream. And the top flow is still circulating like this. So in the next time incident, this recirculating zone has penetrated into the core flow, while the top now starts to. So the flow is oscillating back and forth, the main core flow that is shown, that is sort of blue in color here. So it is changing shape, you can see that. So then the top starts to interact with the core flow and it ejects its vortex. Then the bottom again, the same type of a situation arises. And finally, this is going back to the original cycle here. So this is the type of motion that happens in these 3D, in these unsteady flows. So this, if you plot at a cyclic Nusselt number, if I had a straight channel, when instead of those circular geometry, semicircular arcs, you get heat transfer as a function of time only this much. But once I make the semicircular arc, and then I start to see this up and down Nusselt number type thing, and I'm starting to see that almost 2 times improvement in heat transfer. And that's what is shown here as well as a function of Reynolds number and average Nusselt number, is that initially for low Reynolds numbers, it is same as having flat channel. However, as Reynolds numbers keeps increasing, then you start to see very high performance improvement, and you get close to even twice that of twice or close to 2.5 times that of heat transfer improvement. So that's the and this.
Sir, just one small question here. In the previous graph, so there is it's almost like a sine wave. Does it have any relation with the speed at which the fluid is traveling through the duct?
Yeah, it does have a. I didn't go into those details. It
Okay.
does have a very strong dependence on Reynolds number. Uh, in fact, the speed, Reynolds number meaning the speed of the velocity of the moving stream. You know, there is a critical Reynolds number until you get to that point. You don't see any improvement. It has actually as good as any flat channel. But beyond a critical speed, now it starts to show improvement and starts to actually have a sinusoidal type wave. If you see this time response, it is almost flat, even though it is showing some oscillation here. However, it is almost flat and very little oscillation. If I were to plot Reynolds number at 400, velocity, this is a velocity versus time, you'll see that the response is almost flat. That means there is no unsteadiness in the flow. Right around 500 is where we started to see these fluctuations. And they are not undamped oscillations. They don't keep growing in size. They are quite sustained oscillations. So in some occasions, what does happen is it will show these oscillations and then it will damp out. And then it will again go back to being flat. However, only at a certain critical Reynolds number or certain critical velocity, we start to see these sustained oscillations. That is what we target towards. Did I answer your question?
Yes, sir. Yes, sir. I was just wondering. So, for the example, you had a sine wave kind of a thing in the velocity.
Ah,
It must also be related to the velocity, isn't it? That's what I was just wondering.
yeah, it is very much related. It's
Okay.
a velocity dependent, strong
Yes.
dependence.
Yes. Yes. That's it. Yeah.
You can see whenever you can create a duration of flow, you start to see these type of oscillations. You can have the so-called damped oscillation mode or sustained oscillation mode. So if you are in the damped oscillation mode, that is if the Reynolds number is less than critical Reynolds number or critical velocity, if the velocity is less than that, then you may induce some oscillations. However, it will damp out. So you will not see any particular improvement in velocities. But only when you exceed that critical speed, you start to see these well-defined, well-sustained oscillations. And again, you can show this is another example from the MIT group showing how the sequence happens. So there is pocket of flow that got separated, and then they start to interact. So I'll just that part because I just showed. Now compare these three different geometries that we've been talking about. One is the parallel plate heat sink. So what I'm showing here is thermal resistance versus velocity. As you can see, at a fixed velocity, there are two types of main classification that happens. It's that parallel plate geometry and honeycomb with slots. They are sort of close to each other, while this separating flow and the foam-based heat sinks, they are so are quite close to each other. And the reason is the flow physics are quite different in the parallel plate and the slot and honeycomb, where we are more or less making it streamlined flow. Here, there is a lot of mixing, and the flow packets are getting moved up and down in very unsteady fashion that they seem to behave very similarly. But the story tells even so when you draw graphs for pressure drop across these heat sinks as a function of velocities, you start to see that the parallel plate heat sink has the lowest pressure drop for a given velocity, while the honeycombs are slightly higher. However, what we have shown is that below a certain velocities, the performance improvement of the honeycomb is much higher than better than the parallel plate. So if I want a heatsink based on only pressure drop perspective, that is for a fixed pressure drop, which heatsink gives me better performance, then these honeycomb, slotted honeycomb type heatsinks show better performance. However, if I want something based on pumping power, that is velocity times pressure drop times the area of flow, that is the pumping power of the or fan power, then I don't show that plot here. Then these fin foams show extremely good performance based on pumping power. However, these fin foams, as claimed by someone, Bhattacharya and Mahajan, they don't seem to show any better performance than parallel plate heatsink on equal pressure drop basis. They do incur higher pressure drop. But based on pumping power, they seem. While this flow, one of the geometries that we investigated for unsustained for sustained flow oscillations that show very high pressure drops. They are quite useful only when there is no constraint on pressure drops. For example, in aircrafts where the heat exchanger is mounted at the front, where or in car radiators where the heat exchanger is facing, so it is getting the velocity equal to the speed of the car, where there is no constraint on pressure drop of air. There, these type of unsustained flow oscillations, at least the type of geometry that we investigated, are useful. Otherwise, uh, on equal pressure drop or pumping power basis, they perform poorly compared to parallel plate. So that's I show it here. So you can see that this is the pumping power versus thermal resistance graph. The blue is the unsustained flow oscillation. Parallel plate is shown here. Honeycombs, slaughter honeycombs are here, and fin foams are here. And in fact, we have even shown that it is even better than what is shown here as well. So that's the summary of this advanced heatsink concepts that I thought I'll cover today. And before I move to another topic. Any questions? Otherwise, I'll jump to my next topic.
No, sir.
Okay, thank you. So I guess I have to share it again. So this topic is maybe I should start with the video. So what I'm going to talk about is quite a niche topic on phase change materials, solid liquid phase change materials, as applied to cooling electronics. And I'm sure some of you are well aware of this, but however, I'll just show this. I don't know how well this video will come across. Can you see this video okay?
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir. Video is visible.
Okay, thank you. So here, this is an experiment with solid liquid phase change material. And these phase change materials are good only until they have they are in the solid state. Once the solid becomes liquid, then they don't offer the latent heat. That is so. So they are meant for applications where there are transient, pulses, or for example, they've been explored for batteries these days, where there are a lot of transient pulses or changes in profile, and also where there is a requirement to keep these devices at a certain temperature or below that. So they provide sort of, not necessarily true, sort of an isothermal environment to the device because they melt at a constant temperature. So these phase change material, here's an example where the surrounding is, this is a paraffin wax. It's called icosane. It melts at 36 degrees Celsius. And the surrounding is, this is a cylindrical thing. The surrounding is hot and the bottom wall is being cooled. And this is just an experimental setup. And what you see is that initially there is, so what let me talk a little bit. So if you see that initially this is the hot wall, and the melted material is almost parallel to the hot wall. That means the conduction is the primary mechanism by which heat is being conducted from the hot wall to the phase change material that is white in color. As time progresses, this is the melting front and it keeps moving, and you start to see more and more melting happening on the top than on the bottom because of natural convection effects. Because hotter fluid rises and it carves out more material on the top, and it comes down, it gets cold again, and it again, because of natural convection, rises up and goes to the top. So there's more melting happening on the top, even though we are still cooling from the bottom. That is another additional reason. However, because of natural convection effects, you start to see more melting happening on the top than on the bottom, and eventually they all melt. So this is the principle that we will use to cool some aspects of the electronics, and this I will show two applications in this discussion where we had investigated for motors. There are power electronics for use for motors, and where whenever you start the motor, there is a current inrush, and so the power dissipated is quite high for a shorter duration. But once it reaches a steady state, the power dissipated goes down. So there is a transient pulse that happens. So power is high for a very short duration, and then it goes to a steady state power where the power dissipated is very low value. So we use phase change materials, or we proposed to use phase change materials to absorb that transient pulse. Otherwise, you have to create such a big volume heatsink to absorb, because you have to design the heatsink for the higher power that is happening over a shorter duration. So, so that is unwanted sizing of the heatsink, weight increase, and so on. So phase change material offer a very nice solution in this case to absorb that transient pulse, because you don't keep starting your motor every 10 minutes. So it allows, once the melting is complete, now it will go to a steady state where the heatsink is able to handle that power. During that period, the melted material will re-solidify and will be ready to take up the next starting period. So that's the idea behind this exchange materials. And I will show another example as well, discuss that as well. So if you look at the features of the phase change problem, they are transient problems. They are not steady state problem, because as a function of time, the melting front is moving at a at a speed. So you need to understand the moving boundary aspect of it, and the liquid thermophysical properties are different from the solid thermophysical properties. And in if you are not using a pure phase change material, then you could encounter many different morphologies like dendritic solidification or columnar grains and so on. And on top of it, not just specific heat, now latent heat that needs to be incorporated in the calculation. So if I'm melting, then I have to supply additional heat over and above the specific heat, so that now a solid material can be loosened up to a liquid, essentially make the molecules more movable. That is the liquid state. So for that to happen, for a solid to become liquid, then it has to absorb certain enthalpy. Or if it is uh, solidifying from a liquid state to solid state, then it has to release certain amount of energy. So there is a either latent heat absorption or latent heat release or liberation that happens. So this, I'll skip the example. So we will do a very quick and simple. I won't go into the details. The rather just for this type of problem and get to the application. because these are often covered in textbooks, at least at certain advanced level heat transfer textbooks. So if you see a single solid block which is insulated on the top and bottom, and if you have a temperature T1 at one end and T2 at another end, if T2 happens to be a hotter, then the temperature profile will be a straight line as long as thermal conductivity is constant. So what will end up happening is you will see a straight line. However, if I have two materials, Ka, there is a material A with certain thermal conductivity, and B that has certain thermal conductivity, and again these thermal conductivities are not a function of temperature, then you see that there are different slopes feasible. So that's the aspect of a phase change problem, is that you could have this A being a liquid while this B being a solid. However, at this interface, you will release or absorb latent heat. So that needs to be accounted for. So one can, for this simple case of T1 and T2, we can figure out what is the interface temperature, and that is by saying that TA material will have this type of a distribution and B material will have this type of an distribution, and from this we can back calculate Ti, and that Ti shows up as this. So that's the simplest idea now, where the heat flux in x direction should be equal to, in the A material should be equal to heat flux in the B material. That is the balance that we do. So for when there is no phase change. So if there is phase change, now one has to account for the heat liberated. So heat flux coming in minus heat flux going out should be equal to the rate of heat liberated if it is solidification per unit area of interface. That is the so-called Stefan condition or matching condition at the interface, and it is given by this relationship. Rho is the density of the material, delta H is the latent heat, and ds, S is the location of that interface because it is moving, it is ds by dt, should be equal to the flux in the liquid minus flux in the solid. So this condition is equally valid for whether it is melting or solid, if as long as the material is assumed to be pure material, that is, it is melting at a constant temperature. If it is a binary alloy or a tertiary alloy or quaternary alloy, then one has to really worry about concentration, and there will be liquid as temperature, solid as temperature, and a mushy zone. That we are not talking about. We are just purely talking about a pure phase change material that changes phase from liquid to solid or solid to liquid at a constant temperature. There are binary alloys that are eutectic, so it holds true for binary alloys that are eutectic as well. Eutectic meaning constant temperature. So there are many ways to solve these problems. Simple analytical solutions are available only for simple problems. For complex problems involving natural convection in the liquid region, one has to employ numerical or experimental methods. So the well-known problem that is there is the so-called Stefan problem, and where we assume that there is a blob that is a semi-infinite solid block that is initially at its melting point, and once you at one boundary, this is a semi-infinite medium, and at one boundary you're supplying some hot temperature, and so this melting this material starts to melt. And making some other simplifying approximation, this is how, and if we treat this, because this is semi-infinite medium, we can treat it as a one-dimensional heat flow problem. So once you heat it, call it TH here and T0 here. So at any given instant, at some time instant t, the temperature in the liquid will look like this, because we assumed initially the solid was at melting point. It will be flat. This is how the temperature profile will look like. So because of this assumption that initially it is at some melting point, there is a certain level of simplification that can be done, and the governing equation is transient heat conduction in the liquid region, and we say that the location at which the solid liquid interface uh, is located is the temperature will be the melting point of that, and then we make use of the Stefan condition because there is no, the temperature is at melting point. That means there is no conduction in the solid, so we can ignore the flux from the solid, so you treat only the heat flux in the liquid region. That will be balanced by the latent heat part. Initially, the solid liquid interface at time 0 is at location x equal to 0, and at time equal to 0 and above, for any time greater than 0 as well, the boundary temperature is TH. So that's the boundary condition. So if you solve this problem, then you will get a solution, and it looks very much like the so-called semi-infinite medium heat conduction, except that now semi-infinite medium heat conduction problem, except that now the denominator carries an error function as a function of lambda. This lambda is obtained from the Stefan condition that turns out to be this relationship. It's a transcendental equation. So this can be solved and so on. So I won't spend more time than just rushing through this. So there is a non-dimensional number that naturally arises from this problem. It's called Stefan number. The Stefan number is the ratio of sensible heat to latent heat. So if the Stefan number is small, latent heat is dominating, so the melting front will move slowly. If the Stefan number is large, the melting is happening at a very, very fast rate. So the melting front is moving very fast. That's what it means. So you can solve this analytically only for very simple cases, and that's what I've shown. I will send this notes. So we initially looked up this problem that I just discussed very rapidly is only for melting case. If you want to solve for solidification, the same equation can be used because it's a pure material and the equation remains the same. So there is no change to it. So there is an example as well. I'll skip through that. And there are many complicating factors when you have these phase change problems. You can have natural convection, species concentration, density change, turbulence, and so on and so forth. So we won't get into those aspects, and we'll instead focus on a couple of applications where it sort of gives a better feel for this, where this could be applied. So again, I'm going to play some videos. I don't know if this will work. Okay. You see, there are 3 discrete heat sources that is shown in red, and the phase change material is placed right next to it. And because the gravity is pointing this way, and you see that first initially there is more melting happening from the top, and then eventually it is coming down. So all these walls on the vertical, on the top, bottom, and the side, they are cooled. The heating is happening from these 3 discrete heat sources, and there is a heat spreader that is placed next to it. So this is now sort of like a energy storage device. So when the electronics needs to be operated, needs to start from cold temperatures, then what you do is you store these melted phase change materials, and when it is cold, this melted phase change material will heat up by losing heat. So the electronics will not see a cold temperature during startup. That's the idea behind this, is that the melted phase change material will always see the it doesn't undergo a lot of cold temperatures fluctuations. So you can put these heat sources on the bottom as well, and then you start to see some very interesting natural convection features. These are called Rayleigh-Bénard convection cells that arises where there is an instability that happens, and beyond a certain melted range, then you start to see that the there is initially this 5 or 6 unit cells, they start to collapse into one, and finally it becomes turbulent flow. Here this modeling work was done assuming laminar flow. However, we know that once it becomes a single plume, it was actually turbulent. So we have shown turbulent flows as well. So depending on natural convection in the melt, how you orient it, natural convection will change. If the gravity is pointing this way and the heat source was placed here, then you start to see that more melting happening here. On the other hand, the gravity is same direction, but the heat source is placed on the bottom, so you see a completely different flow physics that is happening. And this bottom heating case is the best case from performance perspective. The vertical wall heating case is not so good. However, the bottom heating case is better. The worst case scenario is having the heat source on the top with respect to gravity being the same in this direction. So now we'll just look into, those are some impacts on natural convection. However, we'll come back to some realistic application. This was a problem that we did with Rockwell automation. Their motors, they had a situation where the motors will dissipate about 600 watts for a period of 25 seconds. Or they could also see in another case 300 watts of heat dissipation for 50 seconds. If you notice, what this is the energy is same. 600 times 25 will give same joules as 300 times 50. So the energy that was input is same. However, the fluxes are different. 600 watts, because the area is fixed, the area is depth not shown in is into the page. The depth is 140 millimeters, and the power is 600, and the height is 70 mm. So the flux is twice in the case of 600 watts compared to 300 watts. And on the right hand side, we have a natural convection cooled system where the heat transfer coefficient is 12 watts per meter square Kelvin and ambient temperature is 40 degrees. So the goal is to see whether using a situation for example, in motor drives, where when we start the motor, the initial torque is so high that there is high initial inrush current. So the power dissipated can be high for a short duration like 25 seconds or 50 seconds. And after that, it becomes a low power that it can be handled by this heatsink itself. So they were using a 10 millimeter thick copper to absorb that high power pulses that are happening. So the goal was to see if we can replace that 10 millimeter, reduce that thickness, and instead use solid liquid phase change material. Okay, so we looked at different materials: bismuth, lead, tin, indium, eutectic alloy. Even though there are 4 different materials, it melts at a constant temperature. Then, however, lead is banned, so we investigated bismuth, tin, and then there was a paraffin, organic phase. These are metallic alloys. These 2 are metallic alloys. The third is a paraffin, which is a triacontane, which had very low, paraffins or organic materials have very low thermal conductivity. I'll show the properties in the next slide. So we used aluminum foam, the stochastic foam that I just discussed on the heatsink part, that the stochastic foams was used as a means of improving the thermal conductivity that triacontane. And so that is the other option, and the baseline material being copper. So these are the properties. So the bismuth, the melting points, copper is just used only for as a heat spreader. It doesn't have. So we wanted to replace this copper with this phase change material. And the bismuth lead indium tin alloy melted at 57 degrees Celsius. The tricontain melted at 65. The leadless alloys at 60, and the tricontain with porous foam will also melt at 65 because tricontain is the exchange material. So if you see, we develop some approximate and exact solutions. I won't get into those things, but let's get to so let's look at this plot. What I'm showing is temperature, because this domain is one dimensional. It is adiabatic on the top and bottom, and you are heating from left side and cooling from the right side. It is one dimensional heat flow. So what I'm showing is temperature profile as a function of location. This is the X location of 10 millimeters. This is the temperature. So the temperature we are expected to keep the device under is 85 degrees Celsius. So the red line is the copper heat spreader of 10 millimeter thick. You can see that for 300 watts 50 seconds it is below 85 degrees Celsius. Also for 600 watts 25 seconds the copper is below 85 degrees Celsius. So it has met the criterion that it will keep it below 85 degrees Celsius copper. However, the goal is to reduce. The copper has a density of 8933 kilogram per meter cube, so it's very heavy for 10 millimeter copper. So they wanted to reduce the weight by using a phase change material. So first we will consider this lead alloy, which is melts at 57 degrees Celsius. You can see this purple line where the melting point of this material is 57. So most of the material is at 57 degrees Celsius. And only up to 2.4, 2.8 mm has melted. And the temperature for this 300 watt 50 second pulse. And the temperature, the peak temperature it has attained is only 61 degrees Celsius, while the copper is at close to 84 degrees Celsius. What you see is that there's almost 24 degree difference or 23 degrees difference between copper and this melting alloy. And also the phase change material has melted only 2.4 mm or 2.8 mm. So the rest of it is not even utilized for this pulse. So you can successfully reduce now the thickness. You can even add a factor of safety and make it even 4 mm, because the lead alloy has the same density as, you can see the property here. The density of the lead alloy is almost same as the density of copper. So you are able to now cut down the thickness significantly. About 6 mm of at least 2 mm can be reduced. And also your junction temperature gets down. That is the advantage of these. As long as you can re-solidify that melted material before the next pulse occurs, phase change materials offer a very distinct advantage over other options that are there. The second is 600 watt pulse. You can still see that leaded alloy, as an example, is that it has melted because of energy content being same. The total amount of melted material is equal. However, the junction temperature changes. So it has melted only up to 2.8 mm, but the junction temperature, because the flux is higher, the junction temperature is close to 65. Still, you get an advantage of 20 degree difference between copper and the phase change material. And it has reduced the thickness required for this heat dissipation. So similarly, we looked at the leadless alloy, that is the blue line, and the green one is the phase change material with aluminum foam. Without the aluminum foam, the phase change, organic phase change contain shot up to 400, 300 degrees. So that's why I haven't plotted here. So without thermal conductivity improvement, the thermal conductivity of tricontain was so poor. You can see the thermal conductivity of tricontain, which is organic phase change material, is only 0.23 watt per meter Kelvin. It's so poor that it's of no use. And the thermal conductivity of the leaded alloy and the unleaded alloy is quite reasonable for the work that we are doing. So that's the advantage of phase change material. And you can compare the two pulses and so on. I will skip these details so that I can get to the next application. The second application that we wanted to look into is a situation where there was a cart going uphill, where there was a power electronic or heat dissipating device that was always dissipating at a constant power. However, when the cart was going up, the velocity of flow that is coming across this heatsink was low. But when the cart was coming back down from the top of the hill back to the foot of the hill, the velocity was high. So the situation when it was coming down, the velocity was high. When it was going uphill, because it was carrying a cargo, it was velocity was low. So then the heat transfer coefficient will be high when it is coming down, while it will be low when it is going up. So here what we did was to again looked phase change material as an option. Instead of designing for this low heat transfer coefficient, we wanted to see if we can make it a hybrid heat sink where the phase change material will be able to compensate for this low heat transfer coefficient region and just use this high heat transfer coefficient as a design for heat sinks. So instead of putting the phase change material close to the heat source, so we wanted to put this phase change material far away, because the heat dissipating device is continuously dissipating a certain power. So this phase change material, once it melts, it cannot resolidify. So instead, if I put it at the tip of the heat fin, then when the velocities are high, I can use that to resolidify the phase change material when it is coming down. But when the velocity is low, the phase change material will melt itself to compensate for the lost heat transfer coefficient. That's the idea that we looked into, and we found that a phase change material does offer such a beautiful situation where you can even absorb, the lower heat transfer coefficient, heat fluxes, and re-solidify so that it can become available for the next round. So the whole trip, so when it is low, it can absorb up to 10 millimeters, 10 minutes of operation. When it is coming down, or when it has to resolidification time was slightly higher to 20 minutes. So you have to either play with the length of the heat sink a little bit and so on to get it close to 10 and 10 sort of, or 10 and 5. So that optimization we did not do. However, we showed that it is feasible to absorb this speed variation as well with phase change material. There are other practical applications of this kind, but I thought I'll just discuss these two things as a way where anywhere you see these transient pulses, phase change materials offer a very good solution.